Okay. Let me welcome everyone to this workshop, to Carnegie Science and to Washington, D.C., here at the peak of our cherry blossom season, which National Park Service and other estimates have predicted to be this weekend and today. So how many of you all have actually gotten a chance to see the blooms? Nice. To let you in on a little secret from the SOC, it was not totally coincidental. We were very hopeful that that would be the case during this workshop. This workshop has been years in the making, about 5 years if you ask Tori Holer, since he started circulating this idea to various RCNs. Decades, several decades, if you ask Steely, from the time he first conceptualized and wrote down the idea of, hey, we need to establish the abiotic background for life detection. And we certainly saw that there was interest from the community in getting together and engaging in this exciting discussion. The intention of this workshop is to bring together experts from relevant fields, which you all represent, from prebiotic chemistry, from origin of life, from mission formulation, technology experts, to assess the state of knowledge in the abiotic background, and equally as important, to understanding the progress that has been made, laying out the gaps and the progress that should be made, and doing this early enough to influence the design and the implementation of missions. And let's keep that in mind as the workshop goes on. Let's keep in mind not just sharing the progress and the ideas that have been successfully published in these fields, but also let's keep in mind the gaps and share with each other the ideas, bring forward the ideas and the knowledge that need to be brought forward. Many of you are parts of fields that are historically underrepresented in the formulation of life detection missions. And so the SOC wanted to make sure that you are given a voice in this workshop. We're framing this conversation around ocean worlds, given upcoming mission priorities and programmatic priorities. But we also wanted to make sure that we bring in the heritage and the lessons learned from those of you in the Mars and early Earth communities, research communities. Significant progress has already been made in addressing the biological potential of ocean worlds and the resulting biosignatures that could be identified there. But not as much has been made in understanding the abiotic end member. So this workshop is intended to facilitate conversations, cross-collaborations, and the community expertise represented by you all, who the SOC saw as critical to this conversation, discussing the abiotic background and its implications for formulation of life detection missions. And Tori and Steely will go into more detail about that in a moment. But first, let me take a moment to give some thanks. I want to acknowledge some of you who have overcome significant travel restrictions to be here with us tonight. Yes. Thank you all. I want to acknowledge SOC members who were not able to be with us in person, but who definitely played a role in realizing this workshop. Alexis Bouquet, Grégoire Donget, and Karen Rogers. Thanks to Carnegie Science, thanks to Steely, thanks to Alicia Alexander and the AV crew here at Carnegie for welcoming us into this great venue. It's ideal for our workshop. And especially you, Alicia, for all the help with the coordination and answering my many questions and just making everything work out, and also for sponsoring tomorrow's refreshments at the poster party. I'd like to thank headquarters for awarding us the TWISC funds, Topical Workshop Symposia and Conferences Proposal Funds, that allowed this workshop to happen. I'd like to thank Brooke Nunn and Enfold for sponsoring our coffee breaks, which I hope you all will see are going to be top notch. I want to thank the 3 RCNs, Enfold, PC3, and Now, for co-sponsoring this workshop with us. And I want to thank Becky McCauley-Renge at NASA headquarters astrobiology program for going above and beyond in her help with travel approval processes. So I look forward to some excellent discussions this week. And with that, I'm going to welcome Steely, and he will say a few words.
I think I have to start off by thanking Svet for a great intro. And all the hard work that she's put in, not only pestering someone like myself who's about as organized as an explosion in a paint factory, but also all you guys and getting you here and making this happen. Tori and I talked about this many years, 20 years, and I was talking with Barbara Sherwood-Lawler about we got this part, abiotic background and life detection against an abiotic background into the Mars program through the NRC report way back. And it's so nice to see it develop to a point now where it's going to be put into use for ocean worlds. Because one of the things that really is the benefit of this, scientifically apart, my work has shown we have abiotic synthesis mechanisms on Mars. Barbara Sherwood-Lawler's work has shown it on Earth. But Barbara has the different perspective than me because she's had to argue that abiosis happens on this planet in the same way that we're having to argue that biosis may have happened on other planets. And it's quite interesting when you look at the juxtaposition between those two arguments, that we're having to fight on two different fronts, if you wish. But the one thing that is absolutely sacrosanct about this scientific approach is there's no wrong answer. If you go to Enceladus and find an abiotic background that is totally awe-inspiring, completely characterizable, is that how life started here? That record has totally disappeared on Earth. We have very, very little understanding of how life started here. So even go, oh, no, we didn't find life. Viking, right? There's no life. Right? No Mars program for decades. Why? Because they were absolutely invested in a yes or no answer. Against an abiotic background, there is no answer. There is only observation and understanding. And that's it. So, and if we do find life, hey, let's patent it, and we'll probably be using it in our cleaning solutions. But that's what's at stake at the moment is the continuation of a beautiful planetary journey that we've been on to understand our solar system and our universe in a way that doesn't only say, are we alone, but where do we come from? And that's, Svet introduced this workshop brilliantly, based on all the things she said. I won't repeat. Now, Carnegie, I'm here to also welcome you to Carnegie. For those of you who don't know, Carnegie is a private research institution. We have our own endowment, set up in 1902 by Andrew Carnegie to be independent of government funding. It's not quite the case, right? We're all living in odd times at the moment. But what we represent is somewhere that you can come, you can be safe, you can think, you can work, and be free. And that's what Carnegie wanted for the Carnegie Institution. And whatever happens, that's what we're going to be here for hopefully many years to come. And also, we're going to reach out a hand to our communities, whatever happens in the years to come. So welcome, enjoy it while you're here. We will be giving tours and stuff like that. You can see all the emergency exits. Loos are through there. The patio is available. Anything on the hill is available. Just go, wander around, sit, make yourself at home. Mia casa, su casa. Think wonderful thoughts under the blossoms and enjoy yourselves while you're here.
Well, I am so glad to see this day finally arrive. As Svet said, this has been a long time in coming together, and it's something that has really been close to my heart for all of that time. So I'm super happy. Can't hear me? I am super happy to see this day arrive. I am so happy that you all are here. And I am so looking forward to learning from all of you. Because that's what this is ultimately about. It's about learning. And the motivation for this workshop really is the realization that as life detection becomes a more and more tangible possibility on missions, there is a conversation that really should be happening and hasn't been happening as much as it needs to. And that is a conversation between the people who understand missions and planetary science and the people who understand all of the diverse things that abiotic processes can do to both contextualize and challenge the way that we will search for evidence of life. And so we've tried to organize the program in a way that really establishes a dialogue. So the first day of our program really is dedicated to understanding ocean worlds, understanding how missions work, understanding the way that people conceptualize life detection approaches right now, and then juxtapose that on the next day with a lot of perspectives about all of the diversity of processes that can happen abiotically that ought to make us think and revisit the way that we do things. And the final day is really dedicated to synthesis, asking you all to take what you've learned on the first 2 days and put it together and think of it in terms of how it ought to impact the way that we think about missions, how the way that we pursue this. So the hopes for the workshop are twofold. The first goal is to generate a paper that comes out of this that really is this community's statement about where we think we are, what we think we do understand, what we think we don't understand, and what are the next logical and sensible next steps in terms to take in terms of research technology development that can best advance us toward the goal of being able to optimize our approach toward life detection. More importantly, for me, there's sort of a social goal as well, and it's to establish a community and a dialogue. So the hope is really to seed a conversation that transcends this workshop, to nucleate a set of interactions that transcend this workshop so that we build a community that considers life detection from both sides, from the biological side and from the abiotic side. And that, to me, if there's one single outcome of this that I hope the most for, it's that one. And we've tried to construct the program in a way that allows for a lot of unstructured time. Part of the reason for having you all eat together, go on field trips together, build in large breaks together, is to allow those interactions to take place. And what I ask from all of you is that you give your ideas and your time and your willingness to be open in that conversation. And if we do that, I think this will be amazing. Because this really is, as a group, when we sat down as an organizing committee and we thought who we would most like to represent these different fields, that is everyone here. Like, everyone said yes, and we were blown away by the formal program, blown away by the people who are coming to take part in this conversation. And so I'm so looking forward to this. I want to again say thank you to Svet. I know that Steely already thanked her, but she's worthy of thanking twice. Every little aspect of both the science organization and the local organization has been in her hands for more than a year now. And so please take the time to, as you see her during the week, extend some appreciation for what she's done, as well to NASA, as well to all of our speakers who have taken the time to meet numerous times leading up to the workshop to coordinate their presentations so that the message best covers the relevant ground. Thank you to the Science Organizing Committee for really devoting their time, their expertise. It was such a marvelous group of people that the only concern was that by putting them on the Science Organizing Committee, they might not be able to contribute in speaking roles. But we broke our rule for that, and so that's the case for many people as well. So we have, in the interest of kicking things off in the best possible way, we've arranged some dinner theater for all of you. We are very fortunate that we will have Morgan Cable and Frank Postberg speak. What we're going to do first is, you've probably noticed that some food has appeared. We're going to ask you all to go ahead, grab some dinner, come settle down, and then we'll bring Morgan and Frank up to the stage. So thank you all so much again for taking part in this.
Yeah, awesome. Okay. Yay. Thank you. Go like this. I'm breaking the freaking, there, okay, it snaps in, I got it. All right, hello, everybody, hello, everybody. All right, so let's kick this off. All right, so I talked about this already. Earth is the exception, not the rule when it comes to outer planets and ocean world. We're finding that most of these oceans are actually underneath crusts of ice. And for some of these worlds, that liquid water may be in contact with the rocky interior of the moon. And we'll talk about why that's important. In other cases, you may have a layer of high pressure ice sandwiched between the liquid water layer and the interior of that world. And they're all interesting to study. If there's one thing that you should take away from this, for those of us who don't live and breathe this every day, I think it's that only by studying each and every one of these ocean worlds and getting an understanding of their diversity and each of their unique features can we really start to address habitability as a spectrum. So there are lots of these, or at least we have evidence that a lot of these moons of the outer planets have liquid water oceans. This isn't even all of them. This doesn't include Ceres. This doesn't include potentially Mimas. There are a few others as well. The Uranian moons, which we hopefully will have a flagship starting, knocking on all the wood next to be able to explore those. And so we're just going to touch on a few key examples here tonight. So I will talk about Europa and Titan, and then Frank will go into wonderful, beautiful, excruciating detail on Enceladus. So first, let's skip out to Jupiter. We've gone 4 AU. Jupiter's 5 AU away from the sun. And the gem of the Jovian system, at least in my opinion, and I think in many others here as well, is Europa. One of the things that's striking about this, if you're a planetary scientist, is just looking at the surface, there are not a lot of craters, right, on the surface of this moon. That tells us that it's geologically young. On average of, 50 to 90 million years, I think, right, guys? Thumbs up. Is that the latest estimates? Yeah. So I always like to say when I give public talks, if T-Rex, had a telescope in his tiny arms and was looking up, he would have seen a very different surface on Europa. And this is important because that means that there could be exchange, that there could be things moving from Europa's liquid water interior and being expressed up on the surface. And that's really interesting for us because this ice crust is on the order of, tens to maybe even 100 kilometers thick. I think what we're guessing the average now is something like 50. Kevin, is that right? I think somewhere around there, 30 to 50. And so it's challenging to drill or dig through that ice. So we're hoping that Europa has these active processes where it can bring some of that ocean water sample and potentially any signatures that it might be hiding in there to the surface or potentially to orbit. Okay, so Europa actually has more liquid water in its subsurface ocean than all of Earth's oceans combined. Now, that may or may not be important for habitability. Certainly, you could envision other places that have less liquid water. Also, as long as the environment is habitable. But again, this is part of us testing that spectrum, right, of these diverse different ocean worlds to be able to understand and characterize these environments that seem to be suitable for life as we know it, potentially some of them life as we don't know it, and really be able to understand that potential in our own cosmic backyard. And Mars is sometimes also referred to as an ancient ocean world because it, of course, was much warmer and wetter in its past. Okay, so why is Europa's ocean liquid, given that it's so far away from the sun? Well, oops, the other video didn't play. We have two processes that we think are going on. One of them is this tidal heating that these videos are showing. Since Europa's orbit around Jupiter is not a perfect circle, and Jupiter, it's the bouncer of the solar system. It's the largest planet. So during Europa's 3.5-day orbit, it gets closer to Jupiter and then further away. And so the entire moon actually does flex, and this tidal friction leads to heating. But we also think that could be radiogenic heating as well. That's the same reason why Earth's interior is warm. Is because of the decay of some of these radioactive elements that also generate heat. So one of the things that Europa Clipper will hopefully be able to do is help us suss out those contributions from these potential different energy sources for keeping that ocean liquid. Now, I wish that this was video footage of Europa or Enceladus, that would be amazing. But no, this is at the Mid-Atlantic Ridge, the seafloor here on Earth. What we find is that when you have these kinds of geothermal heating events, you can have places where like liquid that has been pulled into Earth's interior, heated up, it picks up all these awesome minerals, and then when it flows back out into the very cold ocean waters, it precipitates and forms these beautiful chimneys that have these diverse ecosystems of life that are subsisting as far removed from sunlight as you can get here on Earth, although Barbara can probably tell us of a few deep caves that may be a little bit more isolated. But these are the kinds of environments that we are interested in using as analogs because they're using geothermal, hydrothermal, redox gradient kinds of energy sources instead of, photosynthesis based. And so Europa seems to have these three ingredients for life as we know it: liquid water, chemical building blocks, and an energy source. And so the question is, well, if you have these ingredients for life as we know it, you mix them together and you wait long enough, does life form? Is life just part of the natural evolution of a system? Or is Earth really unique and we are horribly alone in this vast empty universe? Guess which one I hope it is. So very happily, we launched the Europa Clipper mission back in October, right after a hurricane last year. And this is such an incredible spacecraft. Just even the fact that we're, being operating on solar panels, 5 AU away from the sun is awesome. The fact that we're able to host 10 different investigations, so 9 instruments plus gravity science, so actually using the spacecraft to be able to understand all of these processes of Europa. Now, Clipper's main goal is to determine whether or not Europa is habitable, to better constrain that. But to do that, we need chemistry, we need geology and geophysics, we need, our biochemical components as well. We need particles and fields. Every single aspect of planetary science needs to come together to build this picture of what's happening within the crust of Europa, what is being expressed on the surface, how it might be chemically modified during that process, and then once it reaches the surface or beyond. We have these potential evidence of plume activity at Europa that Europa Clipper, if indeed there are plume materials being lofted to elevations where Clipper can fly through, we'll be able to measure those particles. We're also able to measure particles that are sputtered off the surface from micrometeoroid impacts, gases. We're going to do such amazing spectroscopy. We'll be able to, what is the highest resolution image Clipper will be able to get? It was 0.5 meter per pixel, which right now I think you can fit half a school bus into 1 pixel of the highest resolution image we have right now of Europa's surface. So this is really going to revolutionize our understanding of this moon. And the science team has done a tremendous job, not only of making sure that their individual instrument can really contribute in this challenging radiation environment and over the lifetime of the mission, but working together. The remote sensing as well as the in situ instruments, building bridges and having that strong communication early is such a critical part of these any mission really, but especially I think the large teams having those dialogues set up well in advance so that when the data does start to roll in, you're already in that collaborative mode. And we're also preparing for the future. As many of us in the room are well aware, there have been concepts proposed, in particular the Europa Lander concept, to take that next step, to land on the surface, to be able to cut into that really tough ice, that cryogenically cold ice, and do a much more in-depth search for biosignatures that can't be accomplished by a flyby like Clipper is going to do. And so we see this as, starting those chapters and really establishing that case for understanding the provenance, the, how any sort of potential biosignature or the context of that biosignature, how that has evolved and changed as it's been expressed and sitting on this surface. Okay, so that was Europa. Now we're going another 5 AU out to Saturn. And Cassini was the first mission that I ever got involved in. And we all sort of, I think, fall in love with missions, but it's in particular, I think the first one is just such, by the time I joined Cassini, we only had a couple of years left. And so this team had been together for decades. They were like a family. You know, when they were talking about planning sequences of, you know, doing a Titan flyby, someone would say, okay, well, you know, I want to do this observation here. And someone else would say, okay, well, I'll trade you next time. I want to be pointed this way, because Cassini originally was supposed to have a way to be able to rotate the instruments independently of the spacecraft, but they had to descope that because, you know, money. And so the whole spacecraft had to turn if you wanted to point one instrument one way. Anyway, it was an amazing mission. And one of the moons that we learned a lot about was Titan. And here it is actually to scale to Saturn. Titan is actually, if you count its atmosphere, it is the largest moon in our solar system, larger than Mercury. But if you strip its atmosphere away, then Ganymede is slightly bigger. And so we'll give Ganymede that win, because as a chemist, this is just a chemist paradise. I live in LA now, so I'm very familiar with smog, and that's something that is pervasive at Titan. So photochemistry and other processes, Saturn also is quite large. It grabs onto some of these particles from the solar wind and accelerates these protons and electrons and slams those also into molecules of Titan's atmosphere, primarily nitrogen and methane. And it breaks them up into all these sorts of different molecules. Basically, if you are at home and you have your chemistry set, does anyone have one? You know, the ball and stick? Yes, awesome. And so you could make anything that has CH and N, like any sort of combination probably exists in Titan's atmosphere on its surface. And so it makes this beautiful golden haze, which is kind of annoying if you're trying to image the surface or do spectroscopy of the surface, because it makes a lot of those regions where you can do compositional analysis, you can't do that through the atmosphere. But there are a few windows, we call them methane windows, places where the spectrum is transparent. And this is one of my favorite images from Cassini that was collected in the infrared. And what you're looking at here, this is Christophe Sautin always talks about how excited he was to see this. This is specular reflection of a glint of sunlight off of a methane lake at Titan's North Pole. And so this begs to draw parallels between Titan and Earth. They both have thick atmospheres, they both have weather, but that's where the parallels sort of end, because all of the stuff looks the same, but it's made out of very different stuff. Titan has clouds, just like Earth does, but they're made out of methane, ethane, propane, nitriles, all sorts of, you know, very interesting organic chemical compounds, many of which would kill you very quickly. Although, did you know HCN, like the LD50, is larger than you would think? Like, you actually need a larger amount than, I forget, it's like tens of milligrams, I think. It's more caffeine. By volume, like a smaller amount of caffeine will kill you than hydrogen cyanide, by the way. Fun fact. Chemist, talk to me. Okay. But anyway, so we have these molecules that are forming these clouds. They, on Titan, we have rain that etches these beautiful channels in the surface. Now, the surface, we know that the bedrock of Titan is water ice, but we don't know the true composition of this veneer of stuff on top. We actually don't even know how thick that layer is. Some of us in this room have studied this intensively. But it carves these beautiful channels and pools in these lakes, primarily at the poles, that are mostly methane and ethane, a little bit of propane, and they vary depending on whether or not you're at the North Pole versus the South Pole. And these are quite large in volume. Now, from a chemist perspective and a biochemist perspective, you may wonder, gosh, could anything be swimming around in that liquid methane lake? And that's something we'll talk about in a little bit. But again, it's made out of different stuff. The chemistry is different. This is a non-polar solvent compared to the polar solvent that water is. We see evidence that some of these features have dissolved, have been worn away by erosion. And then we also see these gorgeous dunes that we think they're made out of organic bits, but that's as far as our knowledge extends right now. So there is a lot to do at Titan. And we can start to break this apart by process. That's one of the things that I do in the lab here on Earth at JPL, is we try to understand some of these individual mechanisms experimentally and then build up that knowledge so that when we get more in situ data from Titan, we can leverage that understanding. And that's something that I think will be really crucial from an abiotic perspective, an abiotic background perspective, because Titan has such a vast organic chemical inventory. So this is our picture of Titan. By the way, I forgot to mention, it also has a liquid water ocean underneath all of the cool stuff happening on the surface. So if any of you guys are a fan of Star Trek, there was that world that had like the two different liquids. Like we have one for real. It's kind of cool, right here in our own cosmic backyard. And so understanding whether or not there's exchange between that liquid water ocean and the surface. Now Titan is one of these worlds where, based on our understanding, we think there is a layer of that high pressure ice between the liquid water ocean and Titan's rocky or interior that may inhibit or slow down some of those hydrothermal interactions that I talked about, like we envision at Europa and other worlds like Enceladus that Frank will talk about. But it's just such a complex world, really exciting to study. And we're also trying to explore the biochemical potential of that ocean, the liquid water ocean, as well as any potential melt ponds. And so Maya Yanez, who's a student who recently graduated from USC with her, Dr. Yanez with her PhD, did a lot of work looking at various other metabolisms. Because typically, and this is something that I'm sure will come up later on at this workshop, when we try to get estimates of, okay, you've got an ocean world, we're going to send a mission there, we need to know if there's life in that ocean, how much is there, so that we can figure out how sensitive our instruments need to be to detect that life. And so we'll do back of the envelope calculations. Okay, how many cells per mil do we think could be in the ocean of Enceladus or Titan or Europa? And we tend to base those off of methanogenesis for various reasons. One, it's a likely going to be one of the primary metabolisms in a lot of these environments because it's, you know, based off of those redox gradients that we talked about before. But what Maya demonstrated was that things that eat acetylene or that consume other things may also be as abundant or even more so depending on the environment. And so this is something that we should think about as we try to develop these tools and these predictions for cell densities and inform our limits of detection, our requirements for limits of detection of instruments, that we should try to have that agnostic picture. Don't fall on that standard crutch that you always use. So hopefully when you're standing at the shore of a Titan lake one day, you can contemplate these things. In the meantime, though, oh wait, no, I have one more thing before I talk about that. Yes, so the other important thing to note about a lot of these worlds is they're much colder, right? The surface temperature of Titan is 90 Kelvin, minus 183 degrees C. Don't ask me what it is in Fahrenheit. We're scientists, we don't work in Fahrenheit. But the point is that from a chemistry perspective, from a biochemistry perspective, as you cool things down, reactions slow down. In fact, some may stop completely. You can't get over that activation energy barrier. And that's also true for how molecules, how you break and make bonds and the stability of molecules. For life on Earth, you know, covalent bonds tend to be either covalent bonds or hydrogen bonding associations tend to be sort of the language of biochemistry, right? That we make and break that phosphate bond for ATP to ADP to be able to exchange energy, things like that. But on a world like Titan, making and breaking a covalent bond is really hard. There's some ways to do it, but it's really energetically intensive. And so maybe we can take a step back, not fall on those same habits that we're used to with Earth biochemistry and think, well, maybe we don't need a bond that strong to still be able to have that language of and that exchange of energy. Maybe it's something much weaker like van der Waals forces that could take the place of those associations. So that's something to think about as well. This is what I wanted to talk on right before Frank comes up. We are sending the coolest spacecraft ever, an 8-bladed helicopter called Dragonfly, which is launching in 2 years. 2 years, 2027. Oh my God. This is an older video. Now it has 3 helicopter blades on each of the things, which as a triplet, I'm really excited. I like things that come in 3s. But this is really amazing because Titan's atmosphere is so dense. It's 1.5 bar at the surface. And because its gravity is less, it's about 1/6, 1/7 Earth gravity. If you were standing on the surface of Titan and you had wings and you flapped them, you could fly. So it's actually much more efficient to be able to do these flying multi-kilometer hops than it would be to drive like a traditional rover like we do on Mars. So this allows us to be able to explore a lot of different terrain types, on Titan, ranging from Silt Crater, which is where we're landing, so we'll get access to that icy water bedrock, to dunes and interdunes. And what you're looking at here is a percussive drill that can pull samples, basically a fancy vacuum cleaner, into 2 sample cups. One that you can see here will do laser desorption ionization with a UV laser. This is a nice way to get some of those bigger, more fragile molecules into the gas phase, so that we can look for evidence of certain biosignatures and to better understand the complex organic chemistry. The second sample cups, we're basically sticking in a pyrolysis oven. So we're heating it up and we're doing GC mass spec, which we can talk in more detail about later on. And we are bringing with us a chiral column. So if there are chiral molecules, not just amino acids, but alcohols and other molecules, we'll be able to directly address that as a question of whether or not these have been potentially altered by biological processes. Okay, so I have touched on 2 ocean worlds, Europa and Titan. Now I'm going to invite Frank Postberg up to give you an in-depth look at another ocean world, Enceladus. So thank you.
Yeah, thank you, Morgan. I was tasked to first give a broad introduction on Enceladus, because not everyone here seems to be a planetary scientist. And so, and then at the same time, I should go into the details of what we know about the organic chemistry. So I will more and more zoom in into the details, but start like maximum zoom out. There's Enceladus on this, oh, yeah, where the arrow is, that's Cassini image with Sun behind Saturn. And in this configuration, you see the rings in its full beauty. And also the outermost E-ring, which in reflective light is almost invisible. And Enceladus orbits Saturn where the E-ring is brightest. And that was known before Cassini was there. But only then, in 2005, Cassini found out how spectacular the E-ring and Enceladus are connected by this cryovolcanic activity. And these ice particles and water vapor that penetrate the icy crust at the south pole of the moon, they are so fast that some of them overcome the small gravity, relatively small gravity of the moon. And so Enceladus loses ice particles all the time while orbiting Saturn. And that in turn creates the E-ring, which then later evolves dynamically on its own. And because of this cryovolcanic activity, I think Enceladus is the best studied extraterrestrial water environment, because Cassini took advantage that we can sample the subsurface of Enceladus by sampling the E-ring and the plume material. And that's why it's worth to have a full presentation about the organic chemistry on Enceladus. This is this close-up here. Again, a beautiful image. It's like this 4 parallel fractures where the plume is emerging as a curtain actually along all these 4 tiger stripes, sometimes more focused as a jet, but you see that the emission is continuous all over the tiger stripes with some prominent high velocity jets. And some basic parameters, Enceladus is really small compared to Europa, which is about at the same size of our Earth moon. Enceladus is really tiny, just 500 kilometers. You could put it even like on top of Germany, and it wouldn't overlap. It's really tiny. And if it would be a bit smaller, it wouldn't even be in hydrostatic equilibrium. It wouldn't be spherical, but it's just spherical. The density is relatively high compared to the other icy moons of Saturn. Saturn has a bunch of icy moons, and they all have lower density than Enceladus. And the reason is that Enceladus has a larger fraction of rock. So actually 60% of Enceladus roughly is made of rock, and only 40% of water ice and liquid water. The temperatures, we are here now 10 times further away from the sun than Earth. And so on a sunny afternoon at the equator, the sun gives you 75 Kelvin, which is like minus 200 degrees, whatever that is in Fahrenheit. I don't know. No one knows. And so it's even more spectacular. At the poles, you would expect something like 50 Kelvin just from solar radiation alone. And but where these most prominent jets are found, and you can see that on this infrared map, that all the tiger stripes glow basically in the infrared. So heat is emitted in parallel with this emission of matter. And where the most strongest jets are, the temperatures are highest. They're up to 200 Kelvin. So 140, 150 Kelvin hotter than you would expect from solar radiation alone. And the total power of this heat emission is 8 gigawatt. There's also heat emitted in between tiger stripes. Also, the ice in between the tiger stripes is 20, 30 Kelvin hotter than it should be. All right, and then, yeah, Cassini took advantage of this new discovery and could sample the plume material. And because of that, we now understand Enceladus probably better than any other ocean world. And before I go into more detail, or no, the first detail actually I want to present is how we think the plume works, because there's a lot of misconception. In the press, they always talk about geysers. I've even said there's a comparison with Yellowstone. It's something totally different. At least the most simple model we can assume is just the plume is driven by the fact because we have liquid water so close to open space. The icy crust of Enceladus at the South Pole is really thin, much thinner at Europa. It's just 3 to 5 kilometers at the South Pole. The average thickness is larger, so it's 20, 25, 20, 30 kilometers at the equator, but at the poles is thinner, and specifically at the South Pole. And we assume that the crustal cracks can tap the ocean directly through 3 or 4 kilometers of ice, and the icy crust basically swims on top of the ocean. It's almost isostatic. And with that, the water basically rises through 90% or so of the crustal thickness. And with that, is just a few hundred meters away from open space, because here there is no atmosphere. The moon is way too small, the gravity is way too low to keep any gas to speak of. And at the same time, the water is in contact with the surrounding ice. So it's really close to its freezing point, close to 0 degree. But because of the low pressure, open space is just there when you look up. It's also close to its boiling point. In other words, it's close to its triple point. And that's why, even though it's so cold, it steams off like a spaghetti pot at 98 degrees, close to its boiling point here at Earth pressure. And this is basically is the driver of the plume. The evaporation of the liquid water, and the vapor is just sucked into space and accelerated to this tremendous speeds. Within a few hundred meters in the icy vents, the gas ejection speed reaches 1 kilometer per second. That's faster than any usual rifle. And then, of course, also some of the vapor condensates into ice grains. But there's also a second source of ice grains in addition to this vapor condensates, because it's very likely that there are aerosols forming at the water table, because we know that there's a lot of volatile gases in the plume, not just water vapor. There's hydrogen and methane, carbon dioxide, and these gases will bubble up from below. And when the bubbles burst, then they form a spray. There's other sources of aerosols, like the surface is probably very turbulent. The tidal up and down alone is probably 50 to 80 meters or so every day. And yeah, lots of swishing and swashing. So aerosols are basically unavoidable. And they will freeze and will likewise then be entrained in the flow and ejected together with the gas and the salt poor ice grains. And that's the first measurement of Cassini, that we have a very heterogeneous composition of the ice grains. There's this low salinity ice grains that probably represent more the composition of the vapor that has condensed, and then the high salinity ice grains that are likely formed from aerosols and represent better the composition of the water they're coming from. So these are the two instruments, in situ instruments which benefited most from this plume and E-ring sampling: the ion neutral mass spectrometer, INMS on the left, and the cosmic dust analyzer, sampling the ice grains. That's the instruments where I was working with for a greater part of my career and still work with the data. And here, because I only have half an hour or so, a high-level summary about the inorganic substances. That's also part of the abiotic background. From the salty ice grains, we could infer that sodium and potassium salts are the most abundant, like on Earth ocean. But the main difference is that we have this carbonates here, bicarbonate and carbonates in much higher concentrations than on Earth. And they also motivate this high pH value you see there. Current best estimates are 9 to 11, so much more alkaline environment. At the same time, maybe a little less lower salinity. And there's also little SiO2 grains that we could identify in the E-ring, basically, and they are probably messengers from hydrothermal activity at the bottom of the ocean. The plume volatiles, in addition to water vapor, there's a large amount of hydrogen. That was probably the biggest surprise, because you don't expect hydrogen from such a small body, particularly without any atmosphere to speak of. Then ammonia, CO2, and methane. These are the 5 definitely confirmed constituents in the plume. And yeah, hydrogen, I'll come back to that later, is also probably a key indicator of hydrothermal activity at the bottom of the ocean. Then the more recent discovery, that was the knowledge as of 2022. And there are 2 relevant recent discoveries or reanalysis of data of both the CDA and the INMS. First, about the CDA, that was the discovery of phosphates we found. And this is the only spectrum of the cosmic dust analyzer I'm showing. And you can see that the really poor mass resolution this instrument have, because the limitation of the instrument is important to understand. But still, you see this 3 phosphate peaks at the end of the spectrum. They're a unique fingerprint of highly concentrated sodium phosphate salts. And you also see a sodium hydroxide peak. That's, again, evidence of the high pH environment where this phosphate formed from. And we inferred a concentration for the ocean that's a few millimole or so. And this is enormously high compared to Earth, where we have like a micromole, 100 or 1,000 times less than on Enceladus. And when we had that number, we really scratched our head and then, can we publish this? No one will believe us. And then we really went to the lab, actually in Japan at ELSI with Yasu Sekine, and he tried to reproduce the conditions on Enceladus. And then we found actually good reason why Enceladus has this elevated phosphate concentrations. And with that, phosphate was the final of the 6 Schnapps elements. That's why it was a relatively big deal. And the reason why phosphate usually is not soluble or poorly soluble is that it's usually locked up in this calcium phosphates you see on the left, this hydroxyapatite here, or any other magnesium calcium phosphates. That's where phosphate is usually found. And this is a poorly or almost insoluble mineral, unless you put a lot of carbonate in the system. This is shown here. If you put a lot of carbonate in the system, you drive the reaction to the right, and then the calcium rather takes the carbonate. It's probably the only thing that rather likes than phosphate, and releases the phosphate into, or more phosphate can be dissolved into the ocean and charge balanced by sodium. And this buffer system, there are many of these buffer systems, but this buffer system was found to be working in our geochemical experiments, simulating Enceladus. This is, by the way, another way to put what I just said in a nice graphic that was published together with our paper. And this is from our paper showing this. Let's see if this laser pointer works here. Oh, no. But you see, the y-axis is the phosphate concentration, x-axis is the carbonate concentration, and the line you see is the apatite calcite buffer system. That's the reaction you see on top. And you see there's really a correlation, one-to-one correlation of carbonate concentration and phosphate concentrations over several orders of magnitude here. And what gave credibility when Yasu Zecchini reported that this is his favorite buffer system from his experiments was then that the CO2 range, which was previously inferred, total CO2 dissolved in Enceladus ocean, and the total phosphate, this is now the other colored area, really overlap nicely both abundances. So the abundance of carbonate we inferred really not match or allow the high phosphate concentrations we found in the CDA data. Okay, so this was now all about inorganics. Now I will zoom into inorganics. First, in the ice grains, as I said before, there are these two very differently composed pure water ice grains and salty grains. And we can say that because the cosmic dust analyzer can analyze each individual ice grain it encounters. Whereas like the INMS has to scoop up a lot of vapor and then analyze it. Each impact on such an impact ionization time of flight mass spectrometer can be, delivers a spectrum on its own. And that's why we can assess the heterogeneity of both the E-ring and the plume. And the third type now is the organic bearing ice grains. And they are, again, diverse within its group. There are two major, very different archetypes of organic bearing ice grains. One is the high molecular mass grains we published in 2018, and then the low molecular mass grains, which are the specialty of Nozer Cavaja, who also has a new paper in review about this. So yeah, the molecular masses are very different. So the macromolecules are larger than 200 atomic mass units, probably in the thousands sometimes, whereas the light ones are below 100. The concentrations of these grains where we find this macromolecules in is really high. We get a huge signal to noise here. And that's why we have a good handle on the interpretation of the spectra. Concentrations on the percent level, whereas the low molecular mass species show up at much lower concentrations. Yeah, the interpretation, and I go into detail later in the next slide, of this high molecular mass species is macromolecules with both aliphatic and aromatic constituents. And the low molecular mass, they are mostly aliphatic with a few single benzene ring species. Both have functional groups. For the low molecular mass species, they could be better specified from the spectra. Amines, carbonyl, ethoxy, and also probably ether and esters are there. And the solubility is also very differently. Whereas this polar low molecular mass species should be very soluble, this high molecular mass species should be poorly soluble. And now this is a statistics of the spectral peaks we find in CDA for the high mass organics. And there can maybe guide you how we can infer some properties from that. So you see the atomic mass here at the bottom. Top row is 0 to 80, bottom row is 70 to 200. 200 is the end of the spectral recording range of the CDA. Unfortunately, we'll never go back to Enceladus again with such a cutoff. But yeah, CDA was not designed for this task. But the main feature is this repetitive pattern in the high mass range. And you see the spacing between the peaks is 12 to 13. And this is really reminiscent of a high highly unsaturated, a breakup pattern of highly unsaturated molecules. Lots of double bonds, aromatic species. Usually, if you have a saturated, you expect more 13 to 14 the spacing, but here it's 12 to 13. And then in the low mass range in blue, there's some water species that we find in every individual spectrum, telling us that the majority is still waterized of these grains. And then we have some aliphatic species in orange and some heterotomes or mass peaks that require heteroatoms in green. And we find this all in a single ice grain. So you can imagine, okay, it's a mixture of many things, but these ice grains are like a 1 micron in size. And if you put all the organics we see in each spectrum would fit in maybe 100 or 200 nanometer grain. And there is limitations of heterogeneity in such a low space. That's why we prefer the solution that this is all one, well, big macromolecules, and we see the fragmentation patterns of them. So cross-linked macromolecules or even polymers with oxygen and nitrogen-bearing functional groups, where mostly isolated aromatic rings are connected by short aliphatic chains. So the mostly isolated aromatic rings come from this large or very frequent, and if you look in the individual spectra, also very prominent high single to noise benzene peak that shows up in every single of these events. Okay, that's all we can say with the CDA data, and it took us many years and lab analog experiment to reproduce some of these spectral features. And this is like an example, because when I presented this, people, yeah, come on, show us a molecule. And okay, then I showed a molecule. This is a molecular structure that would fit this description. This is, of course, like a biogenic product, but this is by no means a unique interpretation. You can also find molecules that fit the description totally abiotically in a meteoroid. In this case here, the insoluble organic matter that you found in Murchison meteorite. So yes, we know we can sample the complex organic chemistry of Enceladus. It shows up at least in a few ice grains in really elevated concentrations, but CDA cannot really tell us what it means. But the good thing is we can sample it. It's not difficult to sample it. Okay, the low mass organics here, some example molecules that fit the spectral data. Definitely identified the nitrogen-bearing compounds, almost certainly amines. Most probably, or the best fit would be smaller dimethylamines or ethylamines. And the O-bearing compounds are definitely sometimes carbonyl groups like acetic acid or aldehydes. And in the paper, which is currently, Nozer's paper, which is currently in review, hopefully will be published later this year, there's also now new evidence for esters or even ethers in this low mass organic bearing ice grains. So really heterogeneous complexity here. Okay, now organic molecules in the plume gases. The original INMS analysis found methane, I listed that before, and a plethora of candidates for C2 and C3 organics. So again, the spectral resolution and the sampling conditions were such that there's C2 and C3 organics, probably unsaturated species among them, but it was not a unique interpretation. And then there was a recent analysis of the INMS data, AI-aided reanalysis published last year. And they now really, again, not 100%, but very likely confirmed the presence of C2H2. Come on. I mean, a triple bond and alcohols. I mean, they're not, this very likely presence doesn't mean that they're the most abundant in the gas phase. It's just the ones that you could spectroscopically positively identify with the highest confidence. There's another interesting thing that was definitely identified in this analysis, and this is of course highly relevant for organic chemistry, HCN, which, yeah, it's less toxic than caffeine, I learned today. Okay. So yeah, of course, and then we have, remember, we have all this ammonia in the plume. It's almost 1% of the plume gas is ammonium gas. And just to put these two together, you can already synthesize amino acids from that. So it wouldn't be a surprise, just totally abiotically, that just from these two confirmed compounds, so HCN and NH3, they're positively confirmed. You put them together, it's not difficult to create amino acids from that under certain conditions. And then, of course, you can even go further. You do HCN polymerization and go towards prebiotic chemistry all the way. So that's why this HCN is really, I think, for this crowd is a good news, or makes it even more interesting. All right. So yeah, the puzzling thing is that we have methane and CO2 together. So totally oxidized carbonate and totally reduced carbonate. And all these very different species we see here that argue for a strong disequilibrium. So this cannot come from the same source. It's really difficult to imagine. Specifically, HCN is not even stable in water for a few days or so. It's hard to imagine that this comes from the subsurface ocean. All comes from the subsurface ocean. Specifically for HCN, then in this publication, Peter et al., they come up with the idea that HCN actually is and also the alcohols might be a radiolytic product that was produced at the surface. And the reason, and the starting point is basically the plume ice grains that fall down. Most of the grains still fall down as snow at the South Pole. The 90% fall down again, 10% form the E-ring and 90% fall back on the surface. And then they are exposed, of course, to UV radiation mostly. And then, with that, you can easily imagine that you can form HCN. Or you form H2O2 just from the water ice. That would be a source of oxygen. And just with this covering of snow, you will slowly these radiolytic products will sink through the crust 3-4 kilometers within 10 million years or so, or 20, but in a reasonable time, that you can feed back this highly reactive stuff into the near surface waters of the ocean. And that gives you strong redox gradients, which is again a good news for habitability. And also again, CO2 and methane together tells you a story of disequilibrium. Maybe there's different parts in the core of Enceladus where you have serpentinization conditions. On the other parts, you have carbonate formation in the core. All is possible. But anyway, it's just this publication, Wade et al. And Chris Klein, they come up with what we find on Enceladus would work for methanogenesis. All right, now zooming in on the ocean floor now, because that's important, I think, for organic chemistry on Enceladus. And it's a very important fact was the low density of the core. That was done by a very difficult gravity measurement of the Cassini spacecraft. 4 flybys were dedicated to infer the higher moments of the gravity field of Enceladus. And with that, you can infer the density layering structure of the moon. And there was clearly the density contrast between the ocean and the core. So the core could be really well covered with this measurement, and it was much larger than expected. And with that, it must be less denser than expected, 2.3 gram per cubic centimeter. It's really hard to find a rock with such a low density. Specific, and it's totally unimaginable, or very hard to imagine at least, that you have a rocky core with such a low density that's compact. So the by far most plausible conclusion of this measurement was that the rock is not consolidated, and with the low gravity of the moon, that makes sense. On Europa, gravity would quench everything solid, whereas here we have 1% Earth gravity. It would allow some cavities, porosities in the rock. And this is important. because ocean water, there's no reason to stop the ocean water, right? It can percolate inwards. It's not clear how far inward. Probably the density there's a gradient or so, but it's very likely that it can get pretty deep. And this is how the easiest way to create the hydrothermal fluids that I mentioned before, because the tidal forces are much less than on Europa or Io. The eccentricity of Enceladus is much lower. But so it was really hard. People were trying for decades to model how Enceladus can efficiently create heat from tidal forces, and it only started to work with this unconsolidated core, because the tidal flexing on a solid rock, of course, doesn't create that much heat, or it's much harder. You have to really flex the rock much harder than a sandbag. And this is what we have here in the Enceladus core. We don't know if it's really sand or big rocks, but there's friction between the constituents. And with that, the tidal flexing can easily create heat. And with the water flowing through that, you create your hydrothermal fluids. Okay, from the amount of nanosilica we found in the ice grains, we inferred temperatures in the range of 50 to 150 degrees Celsius. And again, from the molecular hydrogen that was found, thermothermalization reactions were indicated. So these are now the evidences for hydrothermal activity. And this is a graphic that shows like a temperature map from modeling. It's totally modeling dependent, but reasonable values. If the fluids can really sink into the core, then it's hottest there, and that reach 200 degrees or even 300 degrees if the permeability is low enough. It all depends on permeability of this porous core. Whereas the hydrothermal fluids that enter the ocean here are on the order of 100 degrees. And this would nicely fit the constraints we got from the nanosilica we had. Okay, so we have all reasons to assume that Enceladus core is an organic reaction chamber of like a very good one. The composition is probably heterogeneous, and any rocky material in the outer solar system, the good analog would be carbonaceous chondrite. So you start already with a few % of well-developed organic chemistry when you form a moon there. We have a wide variety of temperatures and pressures. We have other gradients like pH and redox, and a huge potentially catalytic surface. This is really also important. If you have this porous core with water flowing through it, the rock to water ratio is probably 5 to 1. That would fit the density. So yeah, and with convective flows, pores and bubbles, you can basically choose your conditions for your favorite chemical reaction. You probably find it somewhere there. Okay, now finally, I want to also inform you about what we think, how the organics now get from the ocean to a plume, because it's an important factor if you evaluate the species we find in the plume, how they are connected to the ocean. This is again showing this, a fracture, not to scale, and the little things you see here, these bubbles of volatile gases that would be good carriers of organic material from below, like bubble scrubbing, bringing up stuff, gases and material from below. And then we have this temperature gradient. So here I assume 500 meters, maybe 300, maybe it's 600, not much. And we know the temperature. This is a measurement. So the hot spots where the jets emerge, we have 195, 196 Kelvin. It was measured to the Kelvin. And at the bottom, we have probably 272 Kelvin. So one degree depression because of the salinity. Okay, so now the most volatile organics that are found by INMS in the plume, they bubble up from the ocean below. They're poorly soluble, and they don't care about the temperature gradient. They stay in the gas phase from 272 and cool down 80 degrees. They stay in the gas phase and could basically unaltered enter the plume and the Saturn system from the subsurface ocean, these organics. Then we have the low molecular mass, but with high polarity. They are soluble in the water, but they will exhaust from the gas when they see the low pressure at the water surface. And they would be susceptible to the cooling of 75 to 80 degrees. They reach their condensation point, and that's why these polar low molecular species are preferably found in the ice grains. Or it makes sense that way, because they condense onto the ice grains that form in this icy vent. And then we have the high molecular mass species. They're probably poorly soluble because of this high molecular mass. And we detect them in salt-poor ice grains. And it really was, we scratched our head for some time, but this has to tell us something, that this high concentration of organics, how can they be entrained in salt-poor ice grains? And they have to be solid from the get-go. These high molecular masses, they will be solid under all conditions. They need like 300, 400 degrees Celsius to either melt or become charcoal or whatever. And they come in high concentrations. So the solution to this riddle probably is that they come from an organic enriched layer at the surface, at the very surface of the water table. We took this example from Earth. This happens on Earth all the time. There's biofilm or what it's called? Sea surface microlayer. Okay, and there you don't have, of course, not bubbles of gas from below. That's mostly from waves, entrainment from waves. But it's an important process. So in addition, when these bubbles burst, in addition to the aerosols from the sea, they create pure organic aerosols from this film. They phase separate by the bubble bursting. And here, of course, they get an ice crust, because then they are susceptible to the water vapor that condenses on top of them. And this ice crust is salt poor. So that's why we think how this high molecular mass species are created. So that's the end of this part. High-level summary: even with the limited capabilities of the Cassini instrument, we found a wide range of organics, from very volatile to very large organics, partially highly reactive molecules that are distributed over the gas phase and very differently composed ice grains. And the bottom line is that the next mission can be certain to be able to sample the rich organic chemistry of Enceladus with relatively low effort. And then I hand over to Morgan again. Thank you.
By the way, it is pouring outside. That's what that sound was.
Yeah, no, only
Yeah.
3 slides.
Yeah, you guys are doing great. We're almost done. Just have a little stretch. Okay, there's one last thing that they asked us to talk about, which is to provide a little bit of context for the future landscape of what missions are happening or could be happening. Wow, more lightning. Fun. I left my umbrella in the hotel room. Did anyone else? Ooh. Okay. So I did bring an umbrella. Try to plan ahead. All right. So when it comes to NASA missions, we have 2 slides left. One on NASA missions, one on upcoming ESA missions. All right. So we're almost there. You guys are doing great. When it comes to NASA missions and prioritizations, what happens, the process is about every 10 years, the National Academies for Science, Engineering, and Medicine, NASEM, get together and bring together experts from planetary science, all sorts of fields, over 100 scientists that usually get together in person. This last time, due to COVID, it was all through telecons, 4-hour-long telecons every Friday. Or was it every other Friday? It was a lot, but it was amazing, and got together to discuss and write what's essentially a very thick book that is recommendations for NASA of what science to do and what the prioritization of targets and missions should be for the following decade. That's why it's called the Decadal Survey. And in this, there are 2 flavors of missions that really are important for outer planets. There are other smaller class, and we can talk about how you can try to work some miracles and have a smaller mission go to an amazing place like Triton, which would be cool in the future, but we're not going to talk about that right now. And so there are two classes. There are flagships and New Frontiers missions. Flagship missions, those are the big ones. That's like the Mars rovers, Voyager, Cassini, Europa Clipper is a flagship mission. And for those, NASA says, oh, hey, we're going to this place. Let's say we're going to Uranus. And the science community then forms teams centered around instruments that they would like to put on the payload. And later on, NASA will appoint project scientists who sort of herds the cats, and then when the mission becomes real, they'll select the best instruments they think form, the best payload, and they'll go. For those, the decadal survey recommended that Uranus be the next target for a flagship. So Uranus orbiter and probe is next on the list. But after that, they recognized that Enceladus is important enough that an orbiter and lander, combined spacecraft that could address a lot of the measurements that Frank talked about at Enceladus and look for evidence of biosignatures would be the next priority. Now, a lot can happen between now and then, but we're really hopeful that that prioritization will continue. So that's for flagship missions. Now, going down, New Frontiers missions are cost capped, usually at about-ish $1 billion, which sounds like a lot. It's not a lot. Trust me, it's not a lot. Raise your hand if you've done the Planetary Science Summer School or worked on a mission. Yes, okay, so you all know it's not a lot. But for these, so instead of NASA saying, yay, verily, we're going to Enceladus, instead, NASA says, okay, we have a list of cool places to go. You put your own team together, pick your own instruments, form all of that together, one cohesive mission concept, and then you propose that, and we will pick the best one, maybe two. Usually they'll pick two. I think Kurt said he might pick 3 this next round, but then down select to one that will actually become real and get to go. And for that, there was a list that the decadal survey put out, but then recently, because so many developments have happened, the Committee for Astrobiology and Planetary Science, called CAPS, was asked to do a second assessment. And so that's what you're looking at here. So that's why a few of these things are struck through. They were recommended by the decadal survey, which was in COVID times, so like 5 years ago. And since that time, for reasons that are included in quotes here, don't shoot the messenger. I wasn't involved in that part because I'm very sad. Triton is amazing. Titan is amazing, but just in terms of ocean worlds, the 2 that remain on that list are Enceladus and Ceres. And so these would be, more constrained in terms of science goals because you can't do as much for a New Frontiers mission as you can for a flagship, but still quite compelling and exciting. And the fact that ocean worlds are on both of these lists is really cool and should be celebrated. And so I know a lot of people in this room are involved in developing different concepts to propose for the New Frontier side. A lot of people are involved in beginning to, get the gears turning for Uranus orbiter and probe. And a lot of people have been strong advocates for Enceladus Orbilander for a while. So with that, I'm going to let Frank touch on what's going on with our colleagues across the way. Just click on it.
Oh, okay. Yeah, so ESA is really also moving forward in 2023, the ESA Decadal Survey, which is a decadal survey not just about planetary missions, but all space missions, including astronomy or heliophysics. It's all in one big report. And they recommended a mission to an ocean world in 2022. And then 2024, they announced that they recommend or that they want to go forward with an Enceladus lander mission, which launch readiness in the early 2040s, that will then later land on Enceladus in the early 2050s, because only then there's sun again on the south pole of Enceladus. Doesn't make sense to land there in the 2040s. It's dark. Or it's very dangerous to land there because you cannot really navigate. You don't see where you're going. And that's why this timing so it's the same time scale for the Orbilander. Orbilander also wanted to land 2053 or so. That's like the earliest where you can see enough to land at the South Pole, unfortunately for people of my age. Okay. Yes, and currently ESA is going full steam. They run a science definition team, which results at the end of 26, early 27. And usually ESA is really committed. So I'm part of this definition team. and there was just a meeting last week, they really go full forward with, despite all the challenges. And the only thing is that the budget has to be approved, but this is in contrast to NASA and Congress. This is much easier. Really, because there's a ministerial conference that meets every 3 years. So all of the ministers from each of the member states, and they usually follow the recommendation of ESA. And the concept is really ambitious. So you have to do all this with ESA resources. Keep that in mind. And that's why you have to launch with 2 areas, not just one, but it's not powerful enough. So, and the 2 segments are then assembled in space. Yeah, this is the ESA concept. With solar arrays, because it's ESA, so it's twice as large as Clipper. So it's 50 square meters of solar arrays. Like a huge bird flying to Saturn, going into Saturn orbit. It's a 3-year Saturn orbit phase where you do the flybys of all the other needs. So like this mission is not exclusively focused on in-service, including minus. And clean sampling is also already done with this from Saturn orbit. And then the mission goes into orbit, where clean sampling is more difficult, at least according to the current study. And after about 1 year in orbit, the landing site will be defined, investigated, because from Cassini images alone, you cannot safely land anywhere. And so the mission has to do the reconnaissance before the lander, and then the lander is detached. It's not like the orbit lander where you want the entire spacecraft. It's all opinions, right? So the detention small lander, and that's it. Okay, that was the update from the other side. Thank you.
Hi. And thank you, Frank. It was such a pleasure to co-present with you. This was fun. Thank you all for your attention, especially after eating and traveling. And now it's storming outside, so we'll just keep you in here and do some more Q&A. So if you have questions, please raise your hand. We'll do our best to repeat the questions for those online, and we'll just keep, or we could just pass the mic around. That's even, oh, nice. You guys